Hey guys, it's me, Miss Mills, and welcome to Mrs. Mills' Math Time. The whole point of this video is to help you out with analyzing functions notes. Now, these notes are interactive, so what that means is you do in fact have to watch the video and follow along with the video in order to get answers to the notes and explanations. And once you have all those typed in, you can turn it in for a grade. So this particular assignment, again, you have to watch the video in order to get all of the answers that go along with the notes. So let's go ahead and get started with analyzing functions. So when I'm talking about analyzing functions, that means that I'm going to be looking at a line or looking at a function and just figuring out what does it mean? How can I describe this? How can I write a story from it? So in order to describe or analyze parts of a function or parts of a line, you can either describe them as increasing or decreasing. So that's the first part, increasing or decreasing. So if you describe them as increasing, that means you would have a positive slope. Now, if you describe them as decreasing, that means your slope would in fact be negative. Easy enough, right? The other way you can describe them, or you have to describe them, is it linear or not linear? So remember, for a line to be linear, it has to be a straight line. It cannot have a little curve to it, can't wiggle, nothing like that. It has to be an exact straight line. No funny business. So if there's a curve to it at all, it's not going to be linear. So a straight line has to be linear. So for example, if we're looking at this graph below, and yes, I did make this graph, and yes, I wish I did make it better as well, my bad, but if we're looking at this graph, let's first describe the first red dot, which is at around x equals 0, because here's our x-axis. At around x equals 0 and x equals 4, so the first red dot and the second red dot, how would we describe this? So is it going to be increasing or decreasing, and is it linear or not linear? Well, let's look at it. So from the first red dot to the second red dot, we are moving uphill. If we had a man on the left-hand side and he was walking to the right, he would be walking uphill. So what that means is this is going to be, in fact, increasing. I don't know how that ended up being red, but that should be pink instead. All right. So it is increasing. It is going uphill. And then the second thing that we are focusing on is, well, is it linear or not linear? Is it a straight line or is there a little curve to it? Well, if we're looking at this, especially up here towards the top, it does curve a little bit. There is a curve. It's not an exact straight line. Therefore, in this particular case, it is increasing and it is going to be, it's not typing. There we go. Non-linear. And that's all you have to do. Is it increasing or decreasing? Is it linear or is it not linear? All right. So then if we're looking at the second dots, we have the two blue dots right here from the first blue dot, which is at roughly at x equals 5, and the second blue dot, which is at roughly x equals 6. So from our left dot to our right dot, are we increasing or decreasing? Are we going uphill or downhill? And are we linear or not linear? Well, from here to here, we are going down. If we put a man on the left-hand side and have him walk to the right, in this particular case, it would have been a downhill trek for him. So this would be decreasing. Again, not sure where that ended up being red from. This should be purple. Alrighty, and now we have to figure out, well, is it linear or non-linear? Is it a straight line or is there a curve to it? As you can see, there is a little bit of a curve to it about right here. So since we do have that itty-bitty curve there, that will mean that this is still going to be non-linear. It's not a straight line. All right, so that's all that is. Just if you're analyzing parts of a function, just tell me, is it increasing or decreasing? And is it linear or is it not linear? And that's all you got to do. Now, if we're going to go more into depth when it comes to distance versus time graphs. And the best way to describe a distance versus time graph is they show us how far two objects are from one another at any given time. It describes, how far something is and how long it takes you to get to that to where you need to be. So for example, if we're looking at this particular graph, this one right here, how would we describe it? So what would this line represent on a function? Well, if we're looking at it, as we're moving to the right on the x-axis, which is time is our x-axis, y is our distance. If we're looking at time, as time increases, our distances also increases. This is a positive slope. So what that means is as time goes on, we are moving farther away from our original starting point. So let's say down here at time 0, we were at home. And up here is school. So here's home, here's school. This is the distance between here from home and school. And as time goes on, you are walking to school consistently. There's no breaks, nothing like that. So as time increases, we are moving away from the house. We are moving toward the school. So as time increases, distance also increases from our home because we're heading to school. So how we would describe this line, we would say an object moves away at a constant speed. The reason I'm saying a constant speed is because this particular function is linear. It's a straight line. And when you have a straight line like this, that means you have a constant slope. You have a constant rate of change. You have a constant speed. The slope doesn't change, therefore the speed would be constant. Nothing changes about this line. You're going, you have the same slope the entire time. So that's how you would describe this. As time increases, distance also increases, and an object moves away from the house or wherever we're leaving from at a constant speed. So if we're looking at the next one, well, it's going to be the opposite. Again, home is here and school was up here. This particular graph would represent, well, we were starting at school, and as time increased, we were getting closer and closer to home. Now, I didn't, for some reason, make this line go all the way back home, so I guess we stopped for whatever reason. But in this particular case, as time increases, the distance increases. You're coming back home. You're getting closer to the original starting point. So when also on this line, it is also a linear function. This is a straight line, so that means we do have a constant speed. So what you would say here is an object is moving closer. So coming back home, we're moving closer to the original point at a constant speed because the slope is constant. It is a straight line. So that's how you would describe this graph. Now, this graph in particular, as you can see, as time increases, distance stays the same. It doesn't change at all. So how you would describe this in particular is you would say, well, the object that is moving, it's at rest. It's not going anywhere. So this would be an example of you being at school. So let's say this is home and up here is school. At around 7:40 in the morning, you're at school and you're going to stay here until 3 p.m. in the afternoon. So this is what this would represent. You staying at rest, staying at school the whole day, not coming, getting closer to home, not getting farther away from home. You're staying at a specific place. So how you would describe this is you would say an object is at rest and it's not changing. And I have two more right here. On this one in particular, this one's going to be a little bit different. As we can see, as time increases from here to here, so let's not even focus on this top part right here. Let's just focus on from about 0 to here. Let's focus on that. So I don't like how I did that. Let me do that again. Let's go up a little bit and let's stay there. So as time increases, distance is kind of very slowly increasing. We are slowly getting closer to where, or we're slowly getting farther away from our original standing point. But as soon as we get to like here, something changes. We are getting much farther away at a much faster time. So let's say, for example, this is 0. Let's say this is around 10 minutes. From 0 to 10 minutes, we were kind of at the same place. Let's say in this case, you were walking. You were walking from home to the school. Let's say that. But then at 10 minutes, you got picked up by a friend in a car. And all of a sudden, from the 10 minutes to, let's say this was, I don't know, let's say this was about 15 minutes. from the 10 to 15 minutes, in that 5-minute period, you got so much closer to school, like at a much faster time. So from 0 to 10 minutes, you were slowly getting to school. Let's say you were walking, you were lollygagging, got picked up at around 10 minutes, and then from a friend, and you got to the school at a much faster rate. So how you would describe this in particular is, first of all, it's not linear. This is not moving at a constant slope. The slope does change. It's different. So how you would say is, an object is still moving away. So, going to school. It's moving away from the house, still moving away. And the speed increases. Second spell increases. Make sure I don't mess this up. Increases. And the speed increases. So from 0 to 10, we're moving at a slow pace. And then from 10 to 15, our speed does increase. Our slope becomes a lot more steeper. So that's how you would describe this in particular. And, it's not a constant rate of change. There's not a constant speed. So make sure you would say that when you're describing it. Say the speed does, in fact, increase. It's not constant. And then the very, very, very last one that I'm going to have go with you with, or explain with you, is in this particular case, from here to like here. Let's say that was about let's say that was like 5 minutes. So from 0 to 5 minutes, you were running really fast. Let's say this was you running away from home. You were going on a run. From 0 to 5 minutes, you were sprinting. I mean, your slope is very, very steep. But then at around 5 minutes, you realize, oh man, I'm out of shape. So then you start walking. And your slope gets a lot more stabilized. It starts, rounding off. You start almost not going anywhere. Like from here to here, you're kind of walking, but from here to here, you're kind of, at rest. You're not moving anywhere. So your slope does your slope has a decreasing speed. It decreases from here to here. You're moving really fast away. The slope is steep, but then it kind of becomes a lot more mellow and it starts flattening out. So how you would describe this in particular is, an object is still moving away. We're still running away from the house. But the speed decreases as time goes on. And that's how you would describe that. All right. And the very last slide we have here is, now we're going to kind of apply what we just learned. We're going to start analyzing these functions and putting the correct story with the correct line. So all these are distance to time graphs. That means your x-axis is time. So this is as time increases, and then this is as your distance would increase. So that's all of these right here. And I'll make sure to write that down before I post this. Make sure you know that this is time, this is distance. But we are going to match each distance versus time graph with the correct description. So let's look at this first one. This first one says, Jenna got on the bus at her house. The bus made 2 more stops before it arrives at the school. So what I want you to do is, I want you to pause the video now and think about which one of these graphs would go along with description A. Okay, I kind of feel like Dora the Explorer, but all right, I hope you found the correct answer, and let's go over it real quick. So in this particular case, Jenna got on the bus at her house. So that means she got on a bus, and then it says she made 2 more stops before it arrived at school. So looking at all these graphs, the only ones that make 2 stops, so there's 2 points of rest, is this second graph right here. Jenna, so let's look at it and make sure that this goes with this description goes with this graph. So it says she got on the bus, so she's riding the bus, Jenna's riding the bus, and then there's a stop. We're at rest for a little bit. That could represent the bus stopping to pick up another kid. And then the bus closes the doors and they're on their way back to school again. Oh, well, there's a stop here too. And there's a little bit of time of rest for the kid to get on the bus. And then after that, we are moving on back up to school. So this one would represent A, because it does make 2 bus stops. and she's getting to school. So I would say that this one went along with A. All right. So now we have 2 more graphs left, and let's look at the green description. So this one says Seth and his dad left for school in his dad's car. So they're leaving from home. They got stopped at the train tracker. What the heck? Train tracks for several minutes before they were able to continue to school. So again, pause the video, figure out, is it the first one or is it the third graph? Okay, cool. Again, I feel weird doing that. All right, so I hope you got the correct answer. So this one says Seth and his dad left for school. And then they stopped one time. So they stopped at the train tracks for several minutes, for a long time, before they were able to continue to school, and there was no other disruptions after that. Well, if you looked at these graphs, this first graph would represent the B, because Seth got in his dad's car and they were heading to school. Well, they got stopped for a little bit. This is the first resting point. This could represent them getting stopped at the train tracks. And then after that, they continued on to school and there were no other disruptions, and Seth got to school. So this particular description goes with the first graph. And that's going to be green. Well, no, that's going to be green. There you go. All right, and then as you probably know, the last one goes along with the third graph. So let's talk about that real quick. So it says Antonio leaves for school, but then here something happens. His mom remembered that he left his science project at home. So they have to go back home and grab the project. So they're heading to school. Oh no, they forgot their project at home. So they're heading back home. And then they're at home for a few minutes, I'm assuming, grabbing the science project. And then after that, it says they get back in the car and they head back to school without any stops. They probably race to school because they're probably a couple minutes late. This description does go with this graph because it looks like, you're moving away from home, stopped, you go back home, you're at home for a couple of minutes, and then you head back away, leaving, as time goes on, you're moving farther away from the home. So this would represent the third description. So I would go ahead and say that is description number C. All right, guys, so that's all that goes along with these notes. Let me know if you have any questions. What you're supposed to do after this is you're going to have analyzing functions. I think it's a worksheet. Yeah, function story time activities. So that's what you're going to have to do on Tuesday after you do these notes. Whenever you're finished, typing in all that stuff, make sure that you turn it in for grade. And I'll see y'all later, guys. Bye.